Hi, welcome to this quick video, and in this video I'm going to do both the theoretical and practical introduction to cyclic voltammetry. So in front of me I do have a potentiostat and I have a screen-printed electrode, and I've also got a solution of ferricyanide, which is a kind of classical way of doing a reversible cyclic voltammogram. That said, let me go forward and be quick, or quick with your time. So I have, these are the settings I'm going to use. So this particular potentiostat is controlled by a piece of software called Sense It All, which is available from the Google Play Store or the Apple App Store. And in that software, we actually control the waveform that's used to gather that cyclic voltammogram. So when we choose minus 200 millivolts, what we're doing is setting the start potential at minus 200 millivolts. Then we set the turn voltage at 600 millivolts. So what this means is that the potential is scanned from minus 200 millivolts to 600 millivolts, and then we set the scan rate. Now if we set the scan rate for 100 millivolts per second, it means that to go from minus 200 millivolts to 600 millivolts, 600 millivolts minus 200 is 800 millivolts, so 800 millivolts divided by 100 millivolts means it'll take 8 seconds to go from minus 200 millivolts to 600 millivolts. And then we say that we have because the word cyclic voltammetry is in the title of the method, it means that we actually then go back from 600 millivolts to minus 200 millivolts. And again, that takes 8 seconds. So the whole cycle is 16 seconds. So 8 seconds to go from minus 200 millivolts to 600 millivolts, and then another 8 seconds to go from 600 millivolts back to minus 200 millivolts. So the total cycle is 16 seconds. And when we say repeats here, we mean how many repeats of that cycle do we do. Now today I'm only going to set the repeats at 1. Often when you see published paper, they actually often use like the second cycle or something like that because they get a more beautiful data. But today I'm going to just use 1 cycle or 1 repeat. Now what we will see is, having set those conditions, I'll hit start measurement. And so what you will see is a voltammogram like this generated, and we'll have a look at that. We'll both do the experiment, but this is what you can expect. Now I've also got a simulation here because, you know, the simulation is the kind of perfect. But of course, you know, today we titled this both a theoretical and practical introduction. So things are not perfect, you know, so we sometimes have to interpret non-perfect. So we'll start the potential at minus 200 millivolts, and then the current will change in a non-linear fashion. Now there's an inflection point going from about here to here, and that inflection point, we'll talk about the Tafel equation in a short while. But as we scan the potential, the current is changing accordingly up until a point it peaks. So when it peaks, we'll talk about the Randles-Sevcik equation shortly. And then after that, the current just decreases. People don't talk about that so much, but an equation that can characterize this point is actually the Cottrell equation. What's happening here is that we're applying so much potential to the electrode that unless we do something like rotate or stir or pump, there's not enough material able to arrive at that electrode to keep up with the potential that's being applied. And so we have a depletion zone being built up. And we can characterize that that current due to the build-up of that depletion zone, as I say, using the Cottrell equation. And then we have the turn voltage, where in fact we don't go to 601 millivolts. We stop at 600 millivolts, for example, and then we start scanning in the opposite direction, and cycling back towards the original start potential. And because this case is a reversible system where ferri and ferrocyanide are fairly reversible, then in fact we get the reduction of ferricyanide back to ferrocyanide until we get a peak for the reduction of ferricyanide to ferrocyanide, because it just there's not enough material to keep up with the potential, and then we kind of get that kind of Cottrell response. And if we put repeats on 2, we would just go around the cycle 1 more time. Now I said here that there's an inflection point. So when we're first sort of increasing the potential, there's an inflection point there. Now you'll hear terms like foot of wave analysis, Butler-Volmer and Tafel equation. So foot of wave analysis, I think, is the sort of overarching title, and then you can do sort of something like a Tafel analysis or a Butler-Volmer analysis. But if I was using the Tafel equation, it basically just says that the current is proportional to the potential being applied. And there's no indication of something like diffusion or mass transport, because it's basically saying that we're applying potential and it's not that much potential, and therefore the only limiting factor going on here is the kinetic transfer of electrons. So in that particular equation, you don't find things like the diffusion coefficient, but that will change later on in this. And then we have at the peak here, we have another equation called the Randles-Sevcik equation. Now the Randles-Sevcik equation actually comes from Fick's laws of diffusion, because in cyclic voltammetry, if we're doing nothing but there's no stirring, there's no rotation of the electrode, there's no pumping, then we're under diffusion control. And in that equation, it kind of says that, yeah, the current is proportional to diffusion, or the square root of diffusion. Peak potential, or peak current rather, is proportional to diffusion, or the square root of diffusion, but it's also proportional to the square root of scan rate. So I have done videos on people analyzing electrochemical processes by using different scan rates, and that's often called a Randles-Sevcik analysis. But that current, or that peak current, can be characterized by this particular equation. And now we do have a diffusional coefficient in there, because in fact that peak is in part under diffusion controlled, and as I said, the overall equation is the Randles-Sevcik equation. Now between those two extremes of the foot of the wave and the peak, we have a mixed region where actually both equations I want to say applying, but when I say applying, what I mean by that is at the foot of the wave, it's dominated by something like the Tafel equation, and at the top of the wave, it would be more dominated by the Randles-Sevcik equation. So the weighting of these two equations changes as we go up the wave. As the potential increases, it becomes more and more dominated by the Randles-Sevcik equation, and when we're at the bottom of the wave and the potential is low, we're more dominated by the Tafel equation. So that's why we have the kind of mixed region there. Now after the peak, the current just decreases. Now that decrease can be kind of characterized by the Cottrell equation. What it's saying is there's no potential in the Cottrell equation. It's because the Cottrell equation is under the assumption that there's so much potential being applied to that electrode that everything is under diffusion controlled in this particular case, and so the current is just decreasing with time because we're building up something called the depletion layer. And then there's a point at which actually we then turn and we go back and we start doing the reduction of ferricyanides back to ferrocyanide. Now the next thing I have here is a demo. So what I want to say on the demo front is I will change cameras, and I'll actually do you let's say a demonstration. So I've got the software in front of me. I'll just grab 50. I've got 50 microliters here. To show you how this plugs in. So this is the sensor or potentiostat. This is a 501 carbon electrode. I'll put the 501 carbon electrode in like that. I'll put the solution on. I'll give this a name so we can find it. Ferricyanide 501 I'll call it, so that I can find that shortly. I'll just go back. I will go continue. Minus 600 millivolts, start potential, minus 200 millivolts, start potential, turn potential 600 millivolts, scan rate 100 millivolts per second, repeats just one, the current range 100 microamps, and then I will hit start measurement. Now what we're seeing here is current versus time. So time is tracking along. I can see a little oxidation wave here. And then and then we'll get a little reduction wave. So in fact, here's a little reduction wave, and then it will finish, and then it will be complete, and then it says upload complete. So what we've done then is we've gone from minus 200 millivolts to 600 millivolts back to minus 200 millivolts, and all the time the current was changing according, or at least characterized by those three equations: the Tafel equation, the Randles-Sevcik equation, and the Cottrell equation. Now what I'll do now is just go back to here. It says demo, but then what I could do is I will, when it says upload complete, I'll just do a refresh here. So the way the sensor or potentiostat is acting, it's actually sending all the data in real time to the cloud. So I can see my ferricyanide 501 in here, and we can go in and have a look at the data. So let me just do that. And we can have a kind of look at what kind of voltammogram we got. So this is the voltammetry we got. As you can appreciate, very similar to what we were looking at earlier on. So we have at the beginning, because we start this, even though I've put on ferricyanide, because I started at minus 200 millivolts, it means that ferricyanide actually been reduced to ferrocyanide. So as we scan towards 600 millivolts, we start at this point, there's an inflection point just here. We're starting to oxidize ferrocyanide to ferricyanide, and then we have this mixed region until we peak. And when I said that was sort of defined by the Randles-Sevcik equation, I was doing quite a high scan rate, like 100 millivolts per second. If you reduce that, you'll get more beautiful cyclic voltammetry. But a personal note, I like to do fast scan rates because A, it makes for fast experiments, but it also translates better to faster assays. And most of what the work we do at Zimmer Peacock, or most of our academic collaborators and clients are doing, is actually developing real world assays, so it's good to go fast. Anyway, that said, we peak and then the current reduces as characterized with the Cottrell equation. Then we have the turning voltage, and we go back and we do the reduction now of ferricyanide back to ferrocyanide. So if I was just to do a last summary, so we've defined that cyclic voltammetry is really creating a triangular waveform when we go from minus 200 millivolts in our case to 600 millivolts and back to minus 200 millivolts. And then the current in this semi-reversible system is actually, we're going from ferrocyanide to ferricyanide, and so we get an oxidation wave, and then we go back from ferrocyanide to ferricyanide and we get a reduction wave. And as I say, there's sort of generally three equations that we can apply to characterize that entire curve. If you do have any questions regarding cyclic voltammetry, or you've got ideas for additional videos, please don't hesitate to reach out to us. Okay, thanks very much.